Hey guys, this is section 7.2, and today we're going to be talking about right triangle trigonometry. So the first thing we're going to do today is we're going to talk about how the sides of a triangle relate to an angle. So I'm going to draw a triangle really quickly. And this triangle is a right triangle, indicated by that little L in the corner. And if I call this angle, I'm going to call it alpha. If I let my angle be alpha there, and alpha is just the Greek symbol, it's the Greek letter for the letter A. If I'm talking about this bottom side right here, with respect to alpha, this is called the adjacent side. And adjacent just means next to. So you may be asking why is the bottom the adjacent side, but not this top side here? Well, and that's because that is the side that's opposite of the 90 degree. So if we look to this side, the opposite of the 90 degree, that has a special name. That is called the hypotenuse. And likewise, the side opposite from the angle, that is called the opposite side. So there are three main trig functions. Their names are sine, cosine, and tangent. And you may see them quite commonly abbreviated to sin, which is short for sine, cos, which is short for cosine, and tan, which is short for tangent. And with respect to the angle alpha, sine is the proportion. So sine of alpha, cosine of alpha, tangent of alpha. Sine of alpha is the proportion of how large the opposite side is over how large the hypotenuse is. Likewise, cosine of alpha is a proportion or a fraction that is the proportion the adjacent side over the hypotenuse. And finally, tangent is a proportion of how large the opposite side is over the adjacent side. And so there's a common mnemonic device people use to remember these relationships, and it's sine is opposite over hypotenuse, cosine is adjacent over hypotenuse, and tangent is opposite over adjacent, and this reads as SOHCAHTOA. So you can use SOHCAHTOA to remember which proportions of a triangle go to which trigonometric function. So these are sine, cosine. Let me rewrite that. Cosine and tangent. These are our three trigonometric functions. Not all of them. We'll talk about a few more in a bit. Metric functions. Okay. And so all the trigonometric functions do is give you a proportion of how large one side of the triangle is versus another. So to kind of drive this point home, we're going to do a quick little example with a triangle. So I'm going to draw a triangle here in red, then call this angle here alpha once again, and just choose some numbers. So say this is 8, this is 15, and this is 17. And what I want to do is find what is cosine of alpha, what is sine of alpha, and what is tangent of alpha. So if we go to our cheat sheet up here, and I've just quickly pasted my cheat sheet there. I'm going to take these and move it here. If I want to find cosine of alpha, sine of alpha, and tangent of alpha, well, I know cosine is adjacent over hypotenuse. So my adjacent side would be the side that's next to alpha, but not opposite of my right angle or my 90 degree. So my adjacent side, and what I'll actually do here is I'll create a little key. So my opposite side, my adjacent side, that is going to be equal to 15. My opposite side, that's the side that's opposite of the angle. So you can kind of think of it as like a cannon shooting from the very corner of the triangle. That is going to be equal to 8. And my hypotenuse, the side that's opposite the 90 degree, that is going to be equal to 17. And so since cosine is adjacent, I'm going to shorten it with ADJ over hypotenuse, now I can just simply replace the numbers with my key that I've created here. So cosine is going to be 15 over 17. So cosine of alpha is 15 over 17. Now for sine, that is equal to opposite over hypotenuse. And so using my key, my opposite is equal to 8, and my hypotenuse is equal to 17. Okay, tangent of alpha, that is equal to opposite over adjacent. And with my key, I have 8 over 15. And so there are my 3 trigonometric functions labeled with their values for this specific triangle. So one thing I want to make clear is that I will use a different triangle here. If I were to redraw that a little better, if I were to call this angle alpha instead, then the bottom part of the triangle becomes my opposite. The side that's next to, but not opposite the 90, would become, so this side right here becomes my adjacent. And always the side that's opposite the 90 degree is going to be the hypotenuse. So my hypotenuse. So the opposite adjacent are always relative to what angle you're calling alpha. So in the first case, I called my angle alpha the one on the bottom. So my opposite was 8. My adjacent was 15. And always across from the 90 degree angle will be your hypotenuse. So you can kind of see from the first triangle in red that I drew and the white triangle that I drew, the opposite and adjacent sides kind of flip just depending on which angle you're talking about. Okay, so there are 3 more trigonometric functions. Okay, their names are secant, cosecant, and cotangent. Now, these aren't really super special, but we will just talk about them as well. So secant is hypotenuse. So let me reorganize this really quick. Okay, and you will see secant abbreviated as SEC. Cosecant, which you'll see abbreviated as CSC, and cotangent, which you'll see abbreviated as COT, COT. And secant is equal to, in the proportional sense, hypotenuse over adjacent. And cosecant is hypotenuse over opposite. And then cotangent is adjacent over opposite. And so you might see a pattern here that secant is actually just cosine. So if I had go back to what we had before, remember that cosine of alpha was just equal to adjacent over hypotenuse. Sine of alpha was opposite over hypotenuse. And cotangent, sorry, not cotangent, tangent of alpha was equal to opposite over adjacent. And hopefully you can see the relationship that secant to cosine, cosecant to sine, and cotangent to tangent are essentially the same proportions, but just flipped. And the reason for that is that another way to write it is that cosine, secant of alpha is just equal to 1 over cosine. Cosecant of alpha is equal to 1 over sine of alpha. And cotangent of alpha is just equal to 1 over tangent of alpha. For me, it's a little easier just to remember to flip the proportions, and you have the other three trigonometric functions. If you want to find an easy way, or at least what I think an easy way of remembering which of these three functions go with the three original functions, well, hopefully cotangent and tangent, their relationship is pretty straightforward. But the way I remember how cosecant goes with sine and secant goes with cosine is that if it starts with an S, like secant does, then its reciprocal is one that starts with a C. And if it starts with a C, then its reciprocal is the one that started with an S. So you kind of interchange the letters. To be able to do this, of course, you have to know that sine, cosine, and tangent are the original three. But that will be, I think, pretty straightforward after some time. Okay, so what we're going to do here is we're going to have another triangle and then find the three new trigonometric relationships using proportions. So I'll create a triangle here. I'm going to call my angle alpha. And what I want to find now is secant of alpha, cosecant of alpha, and cotangent of alpha. And so I went around and brought my key that I created from before. And I'll do the same thing as last time where I create a key for my side values. So if alpha is the one in the bottom right, then my opposite side, the opposite, that's going to be 7. The side that's next to, but not opposite the 90 degree, is my adjacent side. So adjacent is equal to 24. And then my opposite side, the side that's opposite from, sorry, not my opposite, the hypotenuse, the side that's opposite from the 90-degree angle, that is going to be my hypotenuse, which is going to be 25. So secant is, looks like I brought down the wrong key. Let me go ahead and fix that really quick. Okay, that looks better. So secant is hypotenuse over adjacent, which is 25 over 24 because adjacent is 24. cosecant of alpha will be hypotenuse over opposite, which we will have as my hypotenuse being 25 and my opposite being 7. And then cotangent, let me make a little room here, is equal to adjacent over opposite. And so that will come to 24 for my adjacent side and 7 for my opposite side. And there are my 3 new trigonometric proportions for this triangle. Hopefully that's a bit straightforward. One thing that I will say is I don't memorize these 3 trig functions in terms of their proportions. For me, it's a bit easier to just think of them as the reciprocals of sine, cosine, and cotangent. That way, if I'm looking for instance, if I'm looking for secant of alpha, so let's say I didn't know that, and I wanted to find secant of alpha, I know that I can just find, so it starts with this S, so I know I can just find cosine of alpha, which I remember to be adjacent over hypotenuse. So if I were to fill that in, that would be 24 over 25. And then just flip the fraction after. So let me take away some of these equal signs that don't necessarily make sense. So if I were looking for secant of alpha, what I would prefer to do is just find cosine of alpha. And then once I figure out what the value is, I would simply just flip the fraction over. And there we go. Now I have my values that match. So hopefully you can see that these two things are actually the same. That's how I prefer to do it. Less things to remember. Just have to remember the relationship between the 3 original trig functions and their reciprocal homies. Okay, so for our next example, I'm just going to draw a triangle, and then we're going to find the proportions for all 6 trigonometric functions. So let's say this is 8. Let's just stick to what we got here, and then we'll call this one alpha. And so what we're going to be looking for is all the trig functions. So sine of alpha, cosine of alpha, tangent of alpha. Then we're going to come over here, find cosecant of alpha, secant of alpha, and cotangent of alpha. And so, well, sine is opposite over hypotenuse. Cosine is adjacent over hypotenuse. And tangent is opposite over adjacent. And then I'll show you a trick, or if you already know the trick, probably won't be too crazy, but we're going to create our key for the opposite side, the adjacent side, and our hypotenuse. So if this is alpha, the opposite side is the one that it goes across to and hits. So our opposite side is going to be 4. Our adjacent side is the one of them that's next to alpha, but of course we know it's not the one that's opposite from the 90 degree, the one from the 90 degree, that's going to be our hypotenuse. And so the other final side is going to be our adjacent side, but we already described how to find that. It's the side next to alpha, but you have to choose the one that isn't already opposite the 90 degree. So that's just going to leave us with 3. And now I can find sine, which is opposite over hypotenuse. Well, my opposite side is 4. My hypotenuse is 5. My adjacent is 3. My hypotenuse is 5. My opposite is 4. My adjacent is 3. And then because I remember that sine and cosecant, remember s turns into a c, all I have to do to find cosecant of alpha is just flip the fraction. So this is just 5/4. Cosine starts with a c. Its reciprocal starts with an s, so 5/3. And tangent of alpha, it's the reciprocal of cotangent is reciprocal of tangent, so flip that fraction and I get 3/4. Now we could go the long way and say, well, cosine of alpha is equal to hypotenuse over opposite. And so our hypotenuse is 5 and our opposite is 4. And so then you can see, like, you could do it that way too. But it's good to remember the relationships that way. You can save yourself some work. Now we're going to quickly prove and talk about two different special types of triangles, which are 30, 60, 90 triangles and 45, 45, 44, 45, 45, 90 triangles. So 45, 45, 90 triangle is a right triangle, excuse my drawing, where both of the two angles that aren't the 90 degree have the same or the same angle, so 45. And so what does that tell us? Well, if we remember from the Pythagorean theorem, a squared plus b squared is equal to c squared. If this angle points to 45 on the opposite, and this one does as well, rather than having a, b, and c as our Pythagorean theorem, technically a and b are both being opposed by 45s. So rather than calling it b, we can just as easily call this one a as well, because they're both being opposed by 45-degree angles. So the Pythagorean theorem simplifies to a squared plus a squared equals c squared. And this shorthand only works if it's a 45, 45, 90. A squared plus a squared is 2a squared. And now to figure out what c is, we take the square root of both sides. And so we get the square root of 2 times a is equal to c. And so now what we have is, rather than having a, b, and c, we got rid of b by kind of being clever and calling it just a because they both opposed 45-degree angles. Now we have another replacement. We can call, rather than calling it c, we can call it square root of 2 times a. And so my new triangle, which is going to be the same exact triangle, just green this time. This side is a, this side is a, and this is the square root of 2 times a. Okay, so there's a little quick formula for 45, 45, 90. And let's do the 30, 60, 90. Let's come up with a simple formula for that. So a 30, 60, 90 triangle, well, to be able to build that proof, just like a square is a perfect rectangle, the equivalent triangle for the square, and so what is a square? Well, it's a rectangle, right? So this is a rectangle. But if the square, a rectangle has all the same side length, so let's say this is 2, this is 2, this is 2, this is 2, we call it a square. It's our perfect rectangle, for lack of a better term. When the triangles all have the same side length, so A, we call that a equilateral triangle. Okay, well, if we split this triangle straight down the middle, now rather than this side length being A from here to here, now that is, and let me give myself a little bit more space. Let's fix that. I'll just redraw this. So if the entire side length from here to here is A, and I drew this line down the middle to the angle, or to the, from the angle down all the way to the other side, this is now half of that distance, right? So from my new line to the end of the triangle is A over 2. Okay, and so now all I really need to find is this side length here, which I will color in green. And remember that all triangles have degrees that add up to 180. So for an equilateral triangle, which I forgot to mention, all of these angles here, let me redraw it with a larger triangle. For an equilateral triangle, since all of them add up to 180 and all the sides are the same length, that means all the angles are also the same length, and they are 60 degrees. 60 plus 60 plus 60, that adds up to our 180 degrees. And because I split this angle straight down the middle, that means this angle and this angle, they're both 30 degrees for these two smaller triangles that I have. And because I drew it perfectly vertically down, that means this is now a right angle, right? And since we know all the triangles add up to 180, well, I have my 90 degree there, and I have a 30 degree there. If I want to figure out what alpha is, and I'm just leaving it alpha for now, I know plus alpha, that has to equal 180 degrees. So 90 plus 30 is 120, plus alpha is equal to 180. Subtract 120 from both sides, and I get alpha is equal to 60. Well, that should match what we already know, because an equilateral triangle is 60 degrees on each angle, which, since we didn't cut this one in half, it should still remain 60. So hopefully that just checks out. So we have that this angle is 60 degrees. Okay, so if we just focus, I'm going to redraw the triangle. If we just focus on that smaller half of the triangle that we have now, we have our 90 degree angle with the bottom having a length of a over 2, or half of a. And then we have the hypotenuse of the triangle, the one that's opposite the 90. Oops, excuse me, didn't mean to click that. Equal to a. Well, if you remember from our original triangle, we have a, b, and c. Really, we just don't know what to call this side. But the formula is a squared plus b squared is equal to c squared, where c squared is the hypotenuse. But our c is called a, so it's going to simplify to a squared. And then a is now a over 2, so it's just a over 2 squared, and then plus b squared, this last side that we don't know. And if we do a little bit of algebra, square this side, we get a squared over 4 plus b squared is equal to a squared. And then we're going to bring all our a's to the same side, so I'm going to subtract a squared over 4 on this side, subtract a squared over 4 on this side. That gives me b squared is equal to be able to do this subtraction. So let me slow down real quick. Go to another page here. So what I have here is I have a squared over 4 plus b squared is equal to a squared. I want to subtract a squared over 4 from both sides. Okay, so these turn to 0. And then I'm left with b squared is equal to a squared over 4. Sorry. Just a squared minus a squared over 4. So I want to subtract these two, but one of them is a fraction and the other isn't, so I need to change them both to be fractions. So a squared is the same as a squared over 1 minus a squared over 4. If I want to subtract these fractions, I need common denominators. To do that, I multiply the bottom by 4 to make it a 4. If I do it to the bottom, I need to do it to the top. And so I get b squared is equal to 4a squared over 4 minus a squared over 4. And so now I can combine these two fractions. So I have 4a squared minus a squared over 4 because their denominators are the same. And then 4a squared minus a squared, that's 3a squared over 4 is equal to b squared. And now to square root both sides, that tells me that b is equal to the square root of 3a over 2. So 2 times 2 is 4. Square root of 3 times square root of 3 is 3. And a times a is a squared. And so just to quickly show you what that algebra looks like, it's b squared is equal to 3a squared over 4. I'm going to square root the left side. I need to square root the right side. The square root of b squared is b. The square root of 3a squared over 4, well, I can change this so that I put each thing in its own square root. This is one of the laws of radicals that you may have learned in algebra. Basically, if things are being multiplied, you can put each of them in their own square root. Well, the square root of 3 doesn't simplify. The square root of a squared is just a, and the square root of 4 is 2. And so you see that these two guys are the same. Just figured I'd show that longhand this time. So we're going to scroll back up. And basically what we figured out is we have another name for b. We can call b square root over 3 of 2a. And so our triangle here, this question mark that we left before, well, rather than calling it b, we can just call it square root of 3 over 2a. And so now we have yet another triangle where everything is basically some number times a. And so you may be asking, well, why did you show us all this? Well, I'm going to redraw the triangles below, and I'll see you in a bit. Okay, so now that I've got these slightly prettier triangles drawn, remember that we said sine of alpha, cosine of alpha, and tangent of alpha. And sine was equal to opposite over hypotenuse. Cosine was adjacent over hypotenuse. And tangent was opposite over adjacent. Go ahead and move these around, give ourselves a little bit more space. Okay, so we have sine of alpha is opposite over hypotenuse, cosine of alpha is adjacent over hypotenuse, and tangent of alpha is opposite over adjacent. So if I let this 60-degree angle, for instance, on my 30, 60, 90, so let's say this one is alpha. Then what I'll have is my opposite side is square root of 3 over 2, a, and my hypotenuse is just a. I'm going to redo that and change the color so it's less confusing though. Okay. And so you'll notice we have an a on top and an I on bottom. So that's actually going to cancel, and we're going to get square root of 3 over 2. And then the adjacent is the adjacent to alpha. If we let the 60 degree be the alpha, our adjacent side is a over 2, and our hypotenuse is a. And so we have an a on top and an a on bottom, so the a's will cancel, leaving us with just, let me see if I can, so this is the same as 1/2 times a over a. So these a's cancel, leaving us with just 1/2. And then tangent of alpha, opposite is the square root of 3 over 2a, and the adjacent is a over 2, which we can write as square root of 3 over 2 times a over 1/2 times a. And so our a's cancel, but also we have 2's on the bottom of each, so our 2's cancel, giving us just the square root of 3. Okay, now I'm going to resize this a little bit, take up slightly less space. And so that was when we chose alpha to be the 60-degree angle. But if we So what I'll do is I'll put this in red to kind of represent that. But in this case, if I choose alpha to be the 30-degree angle and do the same thing, sine of alpha, cosine of alpha, and tangent of alpha, and so all I've really done is just changed which angle I'm calling alpha, then the opposite side of the 30 degree is a over 2 now, and then my hypotenuse is a. So the same thing that will happen before will happen again. The a's will cancel, leaving me with just 1/2. Cosine is equal to adjacent, so that's the side next to but not opposite of the 90. So that would be this guy, that would be my adjacent side. So adjacent square root of 3 over 2a over hypotenuse, which is a. So the a's are going to cancel, just leaving me with square root of 3 over 2. And tangent is opposite over adjacent, so we have a over 2 over the square root of 3 over 2a. Once again, the a's will cancel, and the 2's on the bottom will cancel, giving us 1 over the square root of 3, which we can rationalize by multiplying the top and bottom by square root of 3, giving us square root of 3 over 3. So one thing you might notice is that all I really did was change where alpha was, and you see that sine of alpha was square root of 3 over 2, but now cosine of alpha is square root of 3 over 2. Likewise, cosine of alpha was 1/2 here when I chose 60 degree to be alpha, but when I chose 30 degree to be alpha, sine of alpha was 1/2. So you may notice that it really just depends on what side you call, what angle you call alpha. And we'll come back to this when we fully build the unit circle, in the next section. But basically, sine and cosine, they have some sort of relationship to each other. And if you know the value of sine and cosine, if you know the value of sine, you can find the value of cosine. If you know the value of cosine, you can find the value of sine, because all of these trig functions are interlinked. Now, a lot of the work we did here at the last part is going to be very useful for the unit circle, so it's going to make that lecture a little shorter, which I think you'll enjoy. But realistically, all we really did here was change whether the 60 degree or the 30 degree was alpha. And basically what we have is a triangle that's either tall and has a short bottom, or has a long bottom but a short height. And this would be our, if we had the 60 degree here, and this is if we have the 60 degree here. So if the top one is 60 degree, it'll kind of be this wide one, and if it's the 60 degrees on the bottom, you kind of have this tall one. And this will make more sense when we get to the unit.